All right, let me try another video solution, and actually this is kind of a 2-for-1. I was asked from the harder book, The University of Physics, and it's number 54. It's out of chapter 10. But in our college physics book, it's from chapter 21, and it actually is the same problem. And it's not a surprise. This is the same author or same group of authors who put this together. And then this was a good one that was trying to tie in life science. And, of course, your book does a lot of that. And once in a while, the university physics does a little bit of connection to life science. It's not its main focus, so it's only once in a while. And, of course, when I see them, it's, I get excited and I grab it, not realizing, oh, yeah, I got excited about it before in the other book. So both of these I assigned, and so I guess it's a 2-for-1. You only have to do one of the two, but whichever one you want to say this is the solution to, let's read it. I'll read it out of the university physics book here. It says, but a heart defibrillator being used on a patient has an RC time constant of 10 milliseconds. So that means the resistance times the capacitance is 10 milliseconds. It's due to the resistance of the patients and the capacitance in the defibrillator. So the A says if the defibrillator has a capacitance of 8 microfarads, what is the resistance path in the patient? In other words, R then is the 10, and I'm going to write milliseconds, over a capacitance of 8 microfarads. Now, of course, a farad, and so, well, maybe I better do numbers and units separate here. I'll start with the number. The number is 10 times 10 to the minus 3. And if we divide that by 8 times 10 to the negative 6, we get 1,250. And it will come out to be ohms. Let me kind of prove that to you. Remember, the definition of capacitance is a charge per volt. So this second over a farad would be the units for a farad, which is a coulomb per volt. Okay. Now, this is a perfect opportunity maybe to do something that we don't normally do in math, and that is to take a simple fraction and make it a compound fraction. So let me take the second up here and move it down, because then I get a volt over an amp, and volt per amp is the definition of an ohm. When we say you have a 10 ohm resistor, it means it takes 10 volts in order to get 1 amp to flow through it. Or a 50 ohm resistor would be 50 volts to get 1 amp to flow through it. Anyway, so there the units do work out right. Not a surprise. And then there's the number. All right. So then B, if the initial voltage is 12.0 kilovolts, how long does it take to decline to 6, and that would be 600? So half of its value, it's going to go from 12,000 volts, 12 kilovolts, down to 600 volts. And so this is our decaying exponential that we said a capacitor would have. We could talk about the initial voltage decaying with a time constant. We talked about it really and worked it out in class as a decaying charge. And so notice they would follow the same pattern, and the answer to that is back here, that you can see that, they've got to follow the same mathematical pattern. You can put V on the other side here and see, however Q changes with time, V must change with time, because this is just some constant number. And so there's a different multiplication factor, but other than that prefactor, it's the same exponential decay. So you can say how long does it take for the voltage to decay to half, or you could say how much time does it take for the charge to decay to 1/2. But either way, what you're going to have is 1/2 of the initial, then on this side the initial, and because of that, and we could put in the 12,000. Oh, whoa, my bad. I'm sorry. let me just check my units here. This is 12,000. This is not 6,000. This is 6. Okay, so it is 600. Okay. So it's not half. Okay, so forgive me about the 1/2. That is not half. It's 10 times lower than a half. So that's 1/20th. So we could put a 1/20th here. But maybe we just better put in the numbers. Okay, so we're talking about 12,000 as the initial voltage. And we are then decaying down to 600. And as you can see, 12,000 divided by 600, of course, is, as I said, 1/20th. So with the 600 on top, I would have 1/20th equals to e to the minus t over RC. Now, maybe to simplify that, a 1/20th should be what, 0.05? Yeah. All right. So let me write that as 0.05. And then also let me write this as e to the minus t. And we said the whole time constant was 10 milliseconds anyway. So I might as well just put in the 10 milliseconds for the RC. And of course, now here is where maybe a little higher mathematics, not as tough as our calculus, but we've got to take the natural log. So this would be the natural log of 0.05. And of course, this side would make the minus t over 10 milliseconds. So let me take the natural log of 0.05. That should be a negative number. Yeah, it's about a -3. Okay, so -3 equals a negative t over 10 milliseconds. The two negatives would cancel off. I'll bring the 10 over to here. That makes 30 milliseconds for the time. Yay! All right, so about 30 milliseconds. Okay, good. It wasn't too long of a problem, and it's a 2 for 1. Nice.